Hello, everyone. My name is Maxim. I'm a PhD student at the PFL, and I'm going to present our work on probably robust boosted decision stumps and trees against adversarial attacks. And this is a joint work with Matthias Hein from the University of Tübingen, which was published at NeurIPS last year. So essentially, very briefly about the general setup. So we know that machine learning classifiers are not adversarially robust by default. Essentially, what it means that we have some original image or any input X, and then we add some small change delta, which is specifically chosen, and which is small in terms of some norm. So for example, let's say L2 norm, and we can observe that the prediction of the classifier changes dramatically so that the image gets misclassified with very high confidence in the wrong class. So this is the problem, right? Because intuitively we would expect from a good classifier that small changes in the input should also lead to small changes in the output, right? But here we have the opposite. And this has been a very active area of research particularly for image recognition and for neural networks. And the question that we ask in this paper is, okay, so what about other domains and other classifiers? Precisely about other domains, we mean tabular data. So for example, here is a small example of a fraud detection data set. And essentially, usually it has just some standard features such as age, salary, I don't know, some number of transactions made per week, maximum time spent in some application, and so on. Right? So it's not pixels, it's not words, it's just usual classical tabular data sets. And yeah, so the main idea is that some feature values can be modified, right? So it can be an adversarially crafted change, such as, for example, in fraud detection, where there is usually an adversary, but it can also be some measurement noise or maybe some human mistake. Maybe some value was just mistakenly put in the system. And of course, for high-stake decision-making, it is, in our opinion, necessary to ensure a reasonable worst-case error under possible perturbations of this noise, right? No matter where exactly it comes from an adversary or from some other process. And the expected perturbation range, we assume that it can be specified by some domain expert that knows what is a reasonable adversarial change. Okay, and about other classifiers, we primarily focus in this paper on boosted decision stumps and trees. So the classifier has the following form. So it takes as an input some point X, and it classifies it according to this summation over individual trees. So we have in total T trees in the ensemble, and each tree, so if this is a tree of depth 1, then it's called stump. It's just some function which takes as an input X and returns some prediction according to some set of conditions based on the current input. And we stick to coordinate aligned splits, which means that every split that the tree makes, essentially it is based only on single coordinate. So why is this interesting? Because boosted trees are very widely adopted in practice. So for example, such implementations like XGBoost or LightGBM, they're very efficient and they have been very successfully used in Kaggle competitions. And if you have some tabular data set, then I think it would be fair to say that they are used almost in every such competition with very high success. And another very important aspect, especially for high-stakes decision-making, is that these classifiers are interpretable. So yeah, so I think nobody wants to deploy a black box, so we want to somehow be able to reason about whether the rules that are learned by our classifier, whether they make sense, right? And this is something that we cannot easily do with, for example, neural networks. And this is precisely why we need to look also at something else, some more interpretable classifiers, but which are still expressive in a sense that they can express some complex functions that are of interest in practice. And yeah, so it's very important to develop also robust versions of these classifiers. But first, we would like to understand the reasons of their vulnerability. So kind of what goes wrong? So why do adversarial examples exist for boosted trees? And there's a kind of quite simple explanation. So kind of the intuition can be gained also in some simple 2D example. So what we want to have from a classifier is some geometric margin, right? So it should be reasonable according to, according to some, let's say, domain expert. And this is not something that happens by default. So on the left, we have plotted the outcome of plain standard boosted decision stumps. And we can see that, for example, for this point, this, and this, we can see that the decision boundary goes extremely closely to the points themselves, right? So if there is a small change in these 5 points, then they can be easily flipped to the other side. And yeah, sometimes it's inevitable, but for this data set, for example, we can see that there exists a function which can be expressed by an ensemble of decision stumps, which can robustly separate all these 5 points, right? So it also gets 0 standard training error, but also gets 0 robust training error, right? So which means that it can robustly separate all these points, right? And the key thing here is that just empirical risk minimization alone, just standard boosted stumps in this case, it does not able to distinguish the 2 types of solutions, robust versus standard one. So we need to use a different robust objective. And okay, let's formalize the problem first. So, okay, let's start from what is really an adversarial example. So what do we mean in particular? So if you consider some data point X in RD, and for simplicity, binary labels. So in the paper, we have treatment of the multi-class case, but for simplicity of presentation, we can focus first on binary labels. And we have also classifier F, which maps points from RD to R. And we have some L infinity norm threshold of epsilon. So L infinity norm is the norm that we will focus on throughout this presentation. And the optimal adversarial perturbation is the argmean of this quantity, which is known as functional margin. So it's just the label y multiplied by the output of the classifier. And this is all subject to the L infinity norm constraint on the amount of perturbation that you can make. So this is a very natural formulation, which is very intuitive, because if X is correctly classified, then we know that this functional margin is positive, and essentially X plus delta star will be an adversarial example if X plus delta star is wrongly classified, which means that this happens when this functional margin is less than 0. And how do we measure robustness? We compute robust test error, which is precisely the following quantity. So if the standard test error can be expressed as the average of this indicator function here, so which basically just checks the margin or checks the misclassification, whether y and f of x have the same sign. So instead, we measure robust test error, which is the same, but we also allow this perturbation delta star. Okay, so but the first problem comes from the computational perspective. So finding this delta star is an NP-hard optimization problem, unfortunately, for many interesting classifiers, such as neural networks and tree ensembles. Although exact mixed integer formulations exist, so they can output the optimal perturbation, they are slow and they don't scale to large neural networks or large tree ensembles. Okay, and how do we train robust models in general? So usually we solve the following robust optimization problem. So we minimize over the weights of our model. We minimize the worst case robust loss, which means that we maximize the loss over some perturbation set big delta. Right? So we add this perturbation to the input xi, and essentially we just substitute standard loss by its worst case version. Okay, and so here L is the usual margin-based loss function, such as the logistic loss, exponential, etc. And yeah, exactly, when big delta is just a set that includes only 0, then we just recover empirical risk minimization. So it's strict generalization of empirical risk minimization. And the goal is to really attain small loss, not only at point xi, but for every point xi plus delta, where delta is our perturbation set. And there are two family of solutions. So the first one is known as adversarial training, which aims at approximately solving the robust loss. So which boils down to minimization of the lower bound on the objective, which is not very principled, because if lower bound is small, this may just mean that this lower bound is not tight. So a small value of a lower bound does not tell us too much, actually. And the second family of solutions is probable defenses, which is more principled approach, because minimization of an upper bound. So if you know that an upper bound is small on the worst case loss, then you also know that the true quantity, which is hard to compute, is also small. Okay, so now we'll talk about how to certify robustness and how to perform robust optimization for boosted trees. Okay, so as was mentioned already, robustness certification problem for tree ensembles is NP hard. So this is kind of bad news, but we can derive a tractable lower bound G tilde on G of xy, which is exactly this quantity. And how we can do this is, okay, so we are interested in this optimization problem, right? And what we can, okay, so and if we write down what is our big F of x plus delta, this is precisely summation over individual trees of the ensemble. And we can essentially derive a very simple lower bound just by plugging this minimum inside of the sum, right? So in this case, instead of a single delta for all the trees, we'll have t different deltas which are separate for each tree. Okay, so this is a very simple lower bound. And why lower bound is actually interesting is that if we know that this lower bound is greater or equal than 0, then it means that the true quantity, that is NP hard to compute, is also greater than 0. So which means that x is probably robust. And if the lower bound is less than 0, then it's not conclusive. So it may mean that x is really robust, or it also may mean that it's non-robust. So we cannot say anything. But at least we can count the number of points where x is probably robust, and this will be our guaranteed robust error, which would be exactly an upper bound on the robust test error that we wanted to compute. Okay, and the good news here is that this minimization problem over a single tree, it can be solved exactly just by checking all L leaves of the tree, which can be reached within the L infinity ball around X. So this takes linear time in the number of leaves. Okay, so now we know how to lower bound the certification problem. So kind of the question is, does it help to solve us the min-max problem in order to train robust trees? And actually, yes, because for monotonically decreasing loss function, such as, for example, exponential loss or logistic loss, we have the following property that the maximum loss is actually the loss of the minimum margin, right? And we already know how to solve this, or rather how to lower bound this quantity, which results in an upper bound on the worst case loss. So very briefly, if you fit a new stump, so this is the form of new stump. So it's just we predict one value on the left, and on the right of this step function, we predict essentially WL plus WR. So we really fit a step function which is known as a decision stump. And we fit every new stump in a greedy way when we build a new tree. And it boils down to the following optimization a problem for each stump. So we minimize over the parameters, WL and WR of this new stump. And we minimize the following loss. This G tilde is the contribution of the previous ensemble, and this WL and WR are the ways that we want to optimize. And actually, the observation that we make is that that this minimization problem over here, so it's exactly here. So it can be solved just by a case distinction over the values of B, X, and Y and WR. So we can compute this objective, and we suggest a method how to optimize this using essentially coordinate descent. And the main justification why we can use it and why it's globally optimal, because the robust objective is actually jointly convex in WL and WR. Okay, so this is just a small visualization of the robust objective, so we can see that it is non-smooth, but it is jointly convex in both parameters. Okay, and maybe just a brief note on the computational complexity. So with respect to the number of training points, it is n squared for our method, while for XGBoost, it is n log n. So there is some certain price that we have to pay for robustness here, but I think it's not that much of a price. So it's at least, so n squared is still very scalable for many applications. Okay, and now very briefly about stumps. So why stumps and not trees, not general trees are particularly interesting is that because for boosted stumps, the certification problem can be solved exactly. So, and the proof idea here is that the objective for boosted stumps becomes separable over each dimension. So we can just solve the simple one-dimensional optimization problems, which goes in the following way. So we have the certification problem where we minimize over this delta, and we have the summation of all stumps here. But actually, we can separate this objective according to every dimension separately. So this is the summation of each dimension separately, and we can minimize over delta K, which is the perturbation, just one-dimensional perturbation over dimension K, and we can do this completely independently over each dimension because both the function that we have and also the perturbation set, both of them are separable over dimensions. Okay, and as a result, also the robust loss can be calculated exactly, and we also propose in the paper an efficient update of the ensemble that has to be made within this boosting framework. So I will not cover them here, but all the details are given in the paper. And I think that this is an interesting result because previously exact certification and exact robust optimization were known only for the simplest classifiers such as linear, and in some sense ensembles of boosted stumps are more expressive than linear classifiers, which can be interesting to use in practice. Okay, so now about experiments. Very briefly, so we had around 10 different data sets. So 3 of them are actually taken from the medical domain, from the UCI repository of datasets, and the rest are from image recognition benchmarks such as MNIST, Fashion MNIST, German traffic sign dataset, GTS, and their multi-class versions. So I think it would be fair to say that one should use boosted decision stumps and trees primarily for tabular data, right? And we just include this all these image data sets primarily to compare to the literature. Okay, and briefly, the main summary of the results is the following. Okay, so we have different data sets, and here we have different training methods. And the main metric to compare is RT. So RT is robust test error. This is the exact quantity which we compute using exact mixed integer formulation. And we can see that our robust trees, they achieve the best robust test error compared to the competing methods, basically on all 8 out of 8 data sets. And our fast upper bounds for certification, they are very close to the exact robust test error, which takes a lot of time to compute. Yeah, and with respect to comparison to robust CNNs, for example, convolutional neural networks, we observe that we actually outperform almost all probable defenses for CNNs, even on image classification datasets. So which is kind of quite surprising because convolutional networks are actually particularly suitable for image classification because they were designed to perform this task. And while boosted trees are completely not suitable, right, because they treat every pixel independently. But still, in terms of upper bounds on the robust test error, they are very, very competitive. So we can see that the best method for neural networks achieves, let's say, 8% on MNIST, and we achieve 12%. Right? So it's very close. And maybe this gap can be further reduced. And as conclusions here, first of all, yeah, I think especially based on the last comparison, we can conclude that our robust decision stumps and trees are actually a promising alternative to neural networks if we want to have high probable robustness, right? Especially for tabular datasets. And our results put the infinity probable defense for CNNs, which has been a major topic of research recently, into perspective. And kind of our conclusion is that so far they have achieved only limited success, since comparable performance can be also achieved by such simple classifiers as boosted trees. Simple and not particularly suitable for this task. So just as another baseline to put those results into perspective. Another conclusion is that shallow models that do not have this layer-wise structure, as for example neural networks, that these shallow models, they are easy to certify. Right? So kind of the bound that we derived was very simple, and it was actually empirically very tight. LP robustness for image data, we are not aware if there is really some security applications. So it's more like an interesting research problem, right? But I think for tabular data sets, LP robustness is much more meaningful to consider, especially if you can set some perturbation budget differently for different features, right? So I think this is like really practical setup. So in such applications like fraud detection or robustness to measurement noise, etc., I think this can be very useful. Yeah, and as one of the main conclusions, I think so robustness is a very desirable property, but for really high stakes decision making, we also need to know what happened inside of the model. So interpretability is another very desirable property, and boosted decision stumps and trees are really at the intersection of these two, right? So they are interpretable by default, by design, and we show how to make them robust, right? So I think this is something that is highly relevant in practice for responsible deployment of machine learning models. And okay, finally, I'd like to say that okay, our code is available online, so one can try and train robust boosted trees, and yeah, this should be quite easy to do with this library. And finally, the final slide will be about going beyond probable robustness. So probable robustness is very good, right? So we know that this is kind of the best what we can do, right? So guaranteeing robustness is always the gold standard, but it's not always scalable, especially for large models, which are typically used for image classification or natural language processing. Not all methods, or to be fair to say that none of the methods really scale well to, let's say, ImageNet size or even CipherTen sized models. So, and the solution that we consider in our recent work is a standardized robustness benchmark that does not rely on provable robustness, that relies on more of empirical robustness, but it has two crucial components, which in our opinion are very important for accurate robustness evaluation. So the first one is to use an ensemble of strong attacks from a recent paper from ACML 2020. And the second component is excluding defenses which only make adversarial attacks harder to perform without actually improving robustness. Right. So this is also very important because there has been very long line of research on basically breaking existing defenses. And we kind of collected kind of the most common approaches that just make the attacks harder, but do not provide any additional robustness. And we say that we completely exclude those defenses because they are not very interesting conceptually. And so yeah, so this project is called Robust Bench, and you can access robustness leaderboards for L2 and L-infinity perturbations, and we are actively extending it to other perturbation types. And we also have model zoo here with robust models, so it's very easy to use these models. And we also have a white paper on arXiv that describes the main guiding principles behind the benchmark. And kind of the overall goal here is to really show which ideas actually work for improving robustness. And so just to kind of separate signal from noise and to really understand what really works. Yeah, and contributions are very welcome to Robust Bench. And yeah, thanks a lot for your attention.